and codes. This is something I've been looking into with Thanasis Boulanis. So maybe since these are just two screens, I will just move here. Yeah, so first of all, a code is just a linear code of length 2n over a finite field f is just a subspace of f to 2n. We can equip this space with a Euclidean inner product, and we will be assuming that our code is self-dual with respect to this inner product. Then one can prove that the length of the code is necessarily even and the dimension is half of the length. Now, an important parameter related to code words, so the elements in this vector space C, is a weight of a code word. So this is just the number of non-zero entries that a given code word has. And then one could look, for example, at the minimal weight within the vector space C, and this would be the Hamming weight, and this is an important invariant of the code. But instead, we could also look not just at the number of entries where code words are non-zero, we could also look, when we work over finite fields, how many entries are equal to a given element, and then see how it varies in the whole code C. So then, if you have a code of length 2n, you can associate with it a so-called weight enumerator. This weight enumerator is a homogeneous polynomial of degree 2n of many variables. The number of variables depends on an additional parameter called genus. And this is an invariant of a code. So you don't need to remember the definition of weight enumerator I'm going to give, but this is the most important object for this talk, so you should at least have an idea of how it looks like. So genus G weight enumerator of a code C over a finite field F is constructed in the following way. So we take G vectors in our code C. These are vectors, we put them as columns of a matrix. Now each row has G entries, and these entries are from a field F. So we can take alpha from F to G and ask how many times alpha appears as a row of this matrix. So we put this number as the exponent of X alpha. And then we do it for all the alphas. We multiply the X alpha to a suitable exponent together. We obtain a monomial of degree 2n, because this is how many rows our matrix has. This is the length of the code. And then we get a monomial of degree 2n. And then we sum this over all the possible G tuples that we can take from our code C. And that's the weight enumerator of genus G that we associate to our code. So this definition maybe is kind of confusing at the beginning, and it's not clear what to do with it. But the reason I'm telling you about it is because Brew and Engelhardt, and then later Duke in a more general setting, proved that there exists a homomorphism between the C algebra generated by genus G weight enumerators that one can associate to self-dual binary codes such that the weight of every code is divisible by 4, so that's doubly even. So there is a homomorphism from this space into the space of modular forms whose weight is divisible by 4 and which are invariant under the action of sp2g over z. Now, the way this homomorphism is defined, you take this genus G weight enumerator, and at each variable, at x alpha, you substitute a theta constant. So that's the series that I put here. And then it turns out that this polynomial is a theta series of genus G that one associated to a lattice, lambda, which can be constructed in a certain general way from a code C we started with. And the interesting thing is that for genus 1 and 2, this is actually an isomorphism. But okay, so when we speak of modular forms, we know that these are functions invariant under the action of a certain group. And it happens that there is also a group which act in an invariant way on the C algebra of genus G weight enumerators. So this was proven by Runge for binary codes, and then in much more general setting by Neberens and Sloan. So we are over any finite field F, and then we can prove, well, they proved that the C algebra of this genus G weight enumerators associated to self-dual code over a finite field F of fixed type, so of the same family, these are precisely those homogeneous polynomials in the number of variables that depends on G, which are invariant under the action of a so-called Clifford-Weil group. This Clifford-Weil group depends on a type of the code that here we fix, but in any case is generated by the elements of three types. So the first type just permutes the variables, the second type multiplies the variable by a suitable root of unity, and the third type is Fourier transform or partial Fourier transform. So that's one way to look at it. But we also know that this Clifford-Weil group is isomorphic to a group which is related to symplectic group or orthogonal group. So for this dot here means that, for example, this Z8 cyclic subgroup of order 8 is a normal subgroup of the group on the right, and the quotient is isomorphic to the group on the right. Yes, so with Thanasis Bouganis, taking into account these and many more connections that exist between modular forms and codes, we were asking ourselves, okay, is it possible to apply doubling method in the setting of codes? So in the setting of automorphic forms, what is the doubling method? This is the method that helps us to construct or to associate an L function to a given automorphic form on automorphic representation. And the way this is done is one takes an Eisenstein series of Siegel type and restricts it to a product of two exactly the same groups or two exactly the same subspaces, and takes an L2 inner product with a cuspidal Hecke eigenform. Then, simplifying a bit, this inner product turns out to be standard L function associated to this modular form F times the F itself. And it happens that in the world of codes, within weight enumerators, there is also something like Eisenstein series. So we take a sum over the elements of our Clifford-Weil group, mod out by the parabolic subgroup, which consists of permutation of the variables and multiplication by roots of unity. And then we act via these elements on a certain polynomial that appears in every weight enumerator of a code. This polynomial is like a zero term in a Fourier expansion that one can also define for codes. And then the restriction in this case, where here the variable x, okay, there are many variables, but they are indexed via elements from f to 2g. And then we just write f to 2g as f2g times f2g. And in this way, we get two parameters, alpha and beta, and we get two variables x and y. And then indeed, it turns out that if we take a suitable inner product of this Eisenstein series with certain combination of weight enumerators that one may call a cusp form, there is a definition for that, if this is a cusp form of a certain genus, then it turns out that indeed such an inner product is equal to this cusp form times certain explicit constant. So this explicit constant is there. Maybe it plays the role of some kind of mysterious L function that's hidden in the world of codes, but we don't know yet how it looks like. So now we want to look at this constant and see, okay, can we actually construct an L function and do something with it? So this is basically all I wanted to tell you, but I want to finish with a short announcement. Namely, next year in Poland, I am organizing a 2-week event. First week summer school, second week a conference on automorphic forms and related topics. So this will be in August next year in Poland. There should be website advertised on numbertheory.org in October. Here I give a link to my website. If you would like to know more about the school, please, and the conference, please talk to me. Yeah, thanks.